são, metade do ano que vem.
Você tem mais 6 meses?
Se ela for renovada, sim, mas acho que deve ser. Som? Som? Som?
Som.
Também. Som.
Então, a gente está feliz de receber o Kádmo Laxa para o segundo seminário dessa nova temporada de seminários do NeuroMat. O Kádmo fez doutorado como Antônio Galvez. Na verdade, ele foi, se não me engano, o último aluno do Antônio Galvez. E agora está fazendo um pós-doutorado em Ribeirão Preto sob a orientação do Antônio Roque, se não me engano. Ainda meio no âmbito do projeto NeuroMat. E ele vai falar sobre propagação do caos e transição de fase num modelo estocástico de redes sociais. Ele vai fazer em inglês porque a gente combinou fazer em inglês porque não sei se tem pessoas que não falam português lá no YouTube, etc. Então, é isso.
Okay. Thank you, Morgan, and thank you for the invitation. If you have a problem with the mic, please tell me, Karibe. Okay, so I will talk about propagation of chaos and phase transition in a stochastic model for social network. This is a work in which it's a collaboration with Eva Laxa, and let's start. Okay, so my subject of research is the mathematical modeling of neuronal and social networks. And the framework for this study is the class of system of spiking neurons introduced in Galvez-Laxa. So it's the GL model, that it's a model for system of spiking neurons. And the models of this class are system of interacting pointing processes with memory of variable length. And in a few moments, we will see why they have this name of process with memory of variable length. In a few moments, we will see why. And so in this talk, I will consider a mean field limits for the model introduced in Galvez-Laxa. That is a social network model that it's is inspired by the Galvez-Laxa model, but its aim is to model a social network. And as I said, it is based on a joint work with Eva Laxa. So I will start presenting the model. So we consider a social network with n interacting social actors. We denote AN as the set of actors. And these actors can express opinions along time. And these opinions can be -1, which represent a contrary opinion for a certain subject, and +1, that is a favorable opinion for a certain subject. So at each time t, that it's a positive and real value, each actor A is associated to its social pressure, that it's a real value. Okay, so each actor is associated to a real value, that it's a social pressure, that it's evolving in time. And a point process that indicates the successive times in which this actor express an opinion. Okay, so a set of actors, each actor associated to a real value that changes with time, that it's the social pressure, and also a point process that is indicating the times in which this actor express an opinion. Okay, so this figure here represents what I said. So we have here a graph. The nodes of the graph is representing the actors. The arrows here indicate that in this network, all the actors interact among themselves, and the bars on the side of each actor is representing the social pressure of the actor at a certain time. So here the blue bar is representing a positive social pressure, and the red bar represents a negative social pressure. Okay, so now we will see how the system evolves. Okay, so the actors can express favorable or contrary opinions for a certain subject. And so when an actor expresses a +1 opinion, its social pressure resets to 0, okay? And the social pressure of the other actors increase by age n. Okay, so here age is a parameter of the model, and n, remember that is the number of actors of the system. An actor with social pressure U of A, here a real value for its social pressure, expresses an opinion at rate phi of U of A, okay? So there is a function phi that which indicates the rate in which an actor expresses an opinion based in its social pressure, okay? So here h is a positive parameter, and phi is the increasing function. So here we are considering the case in which the actors, the greater is the social pressure of the actor, the greater is the rate in which this actor expresses a positive opinion. Okay.
Its social pressure sets to 0 means that he does not impact on other participants. That's what you mean, or that he's not impacted by them. In which direction the pressure goes?
Okay, yeah. So when an actor expresses an opinion, its own social pressure resets to 0, right? So we get rid of its own social pressure, but the social pressure of all the other actors on the network changes, and changes on the so here it expresses a +1 opinion. It will change a positive value, and the value that will change is exactly the age divided by n. Okay, so an opinion expressed changes the social pressure of all the other actors of the network, increasing their social pressure, but resetting the social pressure of the actor that expressed the opinion. Okay.
I still don't understand. I'm sorry.
Yeah, also don't understand in which direction this goes.
So when is social pressure is set to 0? When an actor switches from -1 to +1, or all the time that an actor has a +1 opinion?
No, it changes when the actor expresses an opinion. So the actor's express an opinion is not switching the opinion to +1 to -1. It's the point. It's expressing an opinion is at that time the opinion was expressed. So it don't keep track of the opinion that it just expressed. It's somehow that.
So you don't track expressed opinions, and then if it fires, then the social pressure is set to 0, or.
Sorry, can you?
I still don't understand the statement of the model. I'm sorry, but
Okay.
So when an actor expresses +1 opinion, what happens? Is that opinion being recorded somewhere in the history of the process, or is it just setting the social pressure to 0 and no other significance to that?
Yeah. So the opinion expressed in the model, it will cause effect on the social pressure of the actors. Okay. So in the effect that causes on the social pressure is exactly this. An opinion expressed in the model changes the social pressure of the actors on the network. Okay. Resetting the social pressure of the one who expressed the opinion, and increasing by age n.
You are pushing the system to having the same expression that you are imposing. So each time you are saying you have a +1 opinion, you are pushing the system to have +1 also. But then you vanish your opinion. Okay, once I say I have a +1 opinion, I will vanish my pressure, and input some pressure in the other one.
So will you still have an opinion plus or minus one associated with that actor, or?
No, then you vanish the pressure, because
Oh.
we are modeling the pressure.
Yes.
Pressure to have an opinion, to say something.
Right.
Once you say something, you vanish your pressure, but you put some pressure in the other.
On the other. Oh, I see. I got it.
So it means that we model a social pressure, not the opinion of.
Yes.
Yes, yes.
So the social pressure has nothing to do with the
So it's-
opinion that people are going to. The opinion that we express increase the social pressure, but this has nothing to do with the future
We're not
opinions
Yes.
which are going to be emitted in the future by the other actors.
So they actually don't have opinions. They're just forcing each other to express opinion.
They express, yes, they express opinions. So the opinion is a point in the time, and it's not. We are not keeping track of the opinion that the actor have.
But then
It's like so. The idea is that the actor has the social pressure that it's pushing them to express opinion, and they express opinions like they the pressure to express opinion. Now I don't have more this pressure to express an opinion. Now I can go on, and then it keeps receiving opinions from the other actors, and its social pressure keeps changing until the next time it's express an opinion, and then its social pressure is reset to 0 and so on.
and you have similar or symmetric rules for negative opinion.
Yes.
I see.
Yes, yes.
Okay.
This is on the next slide. Yeah, but exactly. So for our purpose, the idea is that we can describe the model by looking just for the social pressure, because the social pressure has all the information that we need to understand the
So
evolution of this.
it's a game of expressed opinions, not real opinions.
Yes, exactly.
Okay.
Okay, thank you. Okay, so this is what happens when an actor expresses a positive opinion. So I have a figure here that, so very quickly here, an actor has this social pressure, and it expresses a +1 opinion with a rate that is the phi of its social pressure, and when it expresses an opinion, its social pressure is reset to 0, okay? And simultaneously, the social pressure of all the other actors of the network increases h divided by n, okay? And as you said, there is a symmetrical way to describe the effect of a contrary opinion expressed on the network, okay? So in a symmetrical way, when an actor expresses a -1 opinion, its social pressure is reset to 0, and the social pressure of the other actor decreases by hn, okay? And so the rate in which an actor with social pressure expresses an opinion -1 is phi of minus u of a, okay? So this is what happens in the model when an actor expresses a -1 opinion. Its social pressure is reset to 0, and the social pressure of all the other actors decreases by hn. So on this picture, I on purpose put the actor with positive social pressure expressing a -1 opinion, because as I said, the phi function is increasing, which indicates that as an actor with positive social pressure has the big express a +1 opinion with bigger rate than a -1, and an actor with negative social pressure express a -1 opinion with a rate bigger than a -1 opinion, but it's still possible that an actor with positive social pressure express a -1 opinion. It's just an event that occurs with a lower probability, but it still can occur, okay?
But so I don't understand very well what is the relation between +1 and -1 still relate to an actual opinion. I'm favorable to this, or I'm not. +1 and -1, it actually represents an actual opinion about something. Like positively, I'm favorable to this, or I'm not, right? So what does that mean for why the fact of emitting an opinion of positive or negative? What does this have to do with social pressure? Why, if somebody expresses a negative opinion, then the social pressure decreases? I mean, from a kind of a modeling point of view or real-world point of view, what's the meaning of this mechanism?
Okay, so from a modeling point of view, the idea is that we have a network in which formed by actors that interact with the others. They care for the other opinions. And the idea is that if the actors, if my colleagues express a lot of opinions in a certain direction, I will have a tendency to express opinion in that same direction. Okay, so in a sense, the social pressure is exactly that the sum of the opinions of the other actors, that the other actors express, that will guide me to express my other opinion, and I will take it in account the opinions expressed to express my opinion. Okay.
The phi function is the same.
Is what?
The same.
Is the same.
It's the same.
Yeah, because and then we have a symmetric thing between the two sides.
I just want to be sure that I'm getting right. In the sense of your comment, it's not that if you say some -1, you are decreasing the pressure of the network. As far as I understand, each time you say a -1, you are increasing the pressure in people which are in red, the people which also have the same opinion that you. Is it right?
No, so the social pressure is a real value, okay? A positive opinion increases the social pressure of the other actors, and the negative opinion decreases the social pressure of all the other actors, okay? So the idea is that if the social pressure is high, it means that the other actors of the network expressed a lot of +1 opinions, and then with high, the tendency of me to express a +1 opinion is big, okay? So in a +1 opinion will just increase the rate in which the other actors express a +1 opinion and decrease the rate in which the actors express a -1 opinion.
So for each point in the network, you have two kind of point processes, one for the +1 opinions and one for the -1 opinions. Is that something like that?
Yeah, but it's like a market point process. You know? A point process that can be a mark +1 or a mark -1 or a 2-point process with one counting the positive opinions and the other the negative opinions.
Okay.
So it means that if your social pressure is positive, he express +1. Yes. And if U is negative, it's express -1 opinion.
Yeah,
Only,
if it's positive, you express with high probability a +1, and if it's negative, you express with high probability a -1.
So it means that if U is positive, he can express -1.
Yeah, but with lower probability. Okay, so. Sorry?
Okay. No, he can. He can.
Yeah, he can.
He
but
can.
with-
He said. He said he can. So phi, if you write phi function, for example.
Yeah, so if you have here the probability of the opinion expressed by a actor being +1, given that, okay, given, this is, okay, the actor that expressed opinion is already peak, and the social pressure of this actor is R. Okay, so let's suppose that we already know that the actor A will express an opinion, and we know that its social pressure is a certain R. So the probability in which the opinion expressed by this actor is +1 is the phi of R divided by phi of R plus phi of -R. Okay, since we are considering here that phi is increasing, we are saying that the greater is the value of the social pressure of this actor, the greater is the probability of expressing a +1 opinion. But it's still there is a probability that it's still possible to express a -1 opinion. There are rates of the point process, but the tendency is that the actors express opinions in the same direction of their social pressures. Okay. But
So phi is so you have for positive opinion you have phi of plus u something, and for negative opinion you have phi of minus, and so this is why you have this symmetrical kind of.
Yes.
I forgot your precedent side, but okay.
Yes. In that, that's the point of the symmetry of the model, because then the probability of express a -1 is we just put a -1 here. Okay, so it.
Phi is symmetric?
No, but the symmetry comes from this division here. Okay, phi don't need to be symmetric. Phi is the rate, so it's positive, always positive.
But in some sense, if you are very negative, you are not having pressure, right? Because phi is very, no?
But
you are not being pushed
if you're very
to...
negative, minus your social pressure is very big. So,
Okay.
so this is
So you are
big.
being pushed to
Yes.
express the same opinion of the...
Like this function, yes, it's positive, right?
No, phi is a positive increasing function, and therefore, if you plug in negative r or positive r in those probabilities, the probability stays the same, but the outcome swap. So it's a absolutely symmetric model in terms of positive opinion and negative opinion.
Yeah.
Because if I have social pressure 20, then with high probability rate 520, I shoot +1, and with small rate 5, -20, I shoot the -1 opinion. If my social pressure is -20, then with high probability 520, which is -20, I shoot a -1 opinion, and with small rate, which is phi of -20, I shoot the +1 opinion. So it's an absolutely symmetric.
No, it's symmetric if phi is symmetric function.
No.
That's the point.
Because this is symmetric.
Positive,
This is symmetric.
That means it cannot be symmetric.
Yeah.
Because you are applying -r. When r there is negative, you are applying phi in -r.
No. In this sense, yes, I understand. But phi, it's the domain of phi is all of the real numbers.
Yes.
But remember that phi has to be always a positive number, okay? Because it is it's a rate.
But the numerator will be always the sign inside the numerator will be always positive. This is the point.
Yeah. The symmetry comes from the fact that the rate in which you express a +1 is the phi of r, and the rate in which you express a -1 is phi of minus.
Yes, this function, if you change.
Yes.
Okay.
Just take the probabilities
Sure.
R for negative R and -1 for positive 1. You'll see that everything works symmetrically.
Yes. Okay. So it's okay? Yeah? Okay. All right. So I explained how the model works. And as I said, the model can be described by the evolution of the social pressures. The actor express an opinion, but if you look at the social pressure, we can see what is happening on the model. It's enough to study the evolution of the social pressures. So we consider here the ut of n as the list of the social pressures at a certain time t. Okay, so it's a vector containing the social pressure of all the actors in at time t. And the evolution of this list of social pressure is a Markov jump process. As we see, so which are the possible jumps, okay? So the possible things that can happen in the model is an actor expressing an opinion, okay? So we have this transformation P A of O that indicate what happened in the model when the actor A expressed the opinion O. And what happens is that it transformed the list of social pressure U for another list of social pressure by resetting the social pressure of the actor that just expressed an opinion, and by summing age n, by summing or subtracting the age n, depending of the opinion expressed, to the social pressure of all the other actors. Okay, so this is just exactly as I told you, the evolution of the model is exactly that. And the rate in which we see these transformations in the model is exactly the phi of the social pressure for a favorable opinion, or the phi of minus the social pressure for a negative opinion. Okay, so we can look to the list of social pressure, and we can describe the model by looking to this, to the evolution of these lists. Okay, so now let's see a simulation of the process. Okay, we consider a simulation with 100 actors. Phi here is the exponential function, and we consider the process with the simulation with two values of age equal to 2 or age equal to 0.5. Remember that age is the value that is added to the other actors when an actor expresses an opinion. Okay. So this figure here is the initial list of social pressure that we consider on our simulation. Okay, so we have here the 100 actors, and here the bar here is represented the initial social pressure of each actor. So the blue bar is representing a positive social pressure, and the high is the value of the social pressure, and the orange bar is represents a negative social pressure. Okay, so let's see the simulation when we start with a balanced situation in which we have half actors with a positive social pressure and half of the actors with a negative social pressure. Okay, so first let's see with age equal to 2. Okay, so what we saw is that initial situation that's balanced is quickly disappeared, and then we have the actors having social pressure in only one direction. In this case, the positive direction, and we see that what usually happens in the model is that the actors are expressing opinion +1, and the actors with high social pressure are expressing opinions. Okay, so we can see again. It began again. Okay. The phi function is the exponential function. Okay, so it's.
It can be also go to down. Yes?
Yes. Yeah. Beginning with this balanced simulation, it has an equal probability to go down or go up.
What is the initial state?
The initial state, and let's just see how I can close this. Yeah, it's this one. Oh, okay, so yeah, this is half of the actors with positive social pressure, the blue, and half of the negative social pressure, the orange.
And the probability to go down, say it's 1/2.
Yes, since it's by the symmetric properties, yes. And so.
What is the H again?
So when
H divided by n.
yeah, it's what you add to the yeah, exactly. Okay, so we can see now the simulation when age is equal to 0.5. And we see that we don't have more this the situation in which the actors have all social pressure in a certain direction. We have that the actors are basically expressing opinions, positive and negative opinions, so we don't have the formation of a majority of social pressure in a certain direction, and it's kind of hard to see, but.
So they need opinions that are low weight.
So yeah, so yeah, AG is smaller, and
It's almost no pressure at all.
yeah, it's almost no pressure. Yeah, but it's not why the case is not that the age is too small. What's happening is that the actors are expressing kind of the same quantity of positive and negative opinions in sequentially. So there is no formation of a big value of social pressure in any direction.
What changed it? You changed age and only age?
Only age.
So this means that now you have an age that is lower compared to the precedent case. So it means that whenever somebody expresses an opinion, it doesn't have much. When age is small, it means that when somebody expresses its opinion, it doesn't have much impact on the network.
Exactly. So yeah, the age is somehow modeling the impact that an opinion expressed by.
Okay.
Yeah, the impact of an opinion expressed on the other actors, on the way the actors choose to express an opinion. Yeah.
Is first age is equal to 1 or 2?
Is equal to 2.
2 and this
1/2.
1/2. Okay.
Yeah. Yeah. Yes.
Maybe it's a question that you will speak in a few minutes, but you are saying that you have two different kind of regimes, right?
Yes.
And it's not something about the scale that you are looking at. I mean, in the h equal to 2, it's not that if we wait for long enough, you can have like, okay, maybe you are in the blue consensus, but if you wait enough, you can go to the yellow one. Because this is more or less what's happening when you have a small h, right? It seems to be, or
no, yeah.
So am I speaking something?
So the behavior that we see in simulation, then later we will discuss the results. But basically that. So the age equal to 2 means that we quickly have a formation of what we could call a consensus. That the social pressure all in a direction and opinions majorly being expressed in a certain direction.
My question is this like a?
It's not a time scale. It's not the time scale. So.
Not time.
No, it's not the.
Okay,
the
this is my
scale,
question.
No,
so
no.
Your consensus in the first scenario is like you are going to some stable state and you stay in there, right?
Exactly.
Okay.
Yeah, yeah. No, it's not.
Why not? I think yes, because if you take h is equal to 2 and you take a number of actors 4 times 100, I think it will be the same effect, not?
No, it won't be the same effect, and we can.
Maybe this is the result. I think this is his theorem.
Oh, you're.
I should be theorem.
Yeah,
Okay.
I think this is the theorem that you are asking.
Okay.
Maybe I don't.
No, it's one of the theorem. Or going from this, we can see this here. So if you simulate a lot of. So this is okay. So we have now more actors, 1,000 actors. We have the same phi and the same age. Age is equal to 0.5, and we take different simulations and we look to the mean social pressure. So we sum all the social pressure, divide by the number of actors, and see how this evolves in time for different simulations. Okay. So for the second case, in which age is low, is small, we see that okay, even if you start with the actors with social pressure in a certain direction, in the minus direction or in the plus direction, this mean social pressure will be quickly close to 0, where it stays on a stable situation. Okay, and if you do the same thing to age equal to 2, we see that even when we start in a situation in which the social pressure is close to 0, in a few steps, the simulation will close. Will be the mean social pressure will be to either positive value or value that is symmetric to this one. Okay, so it's really, it's not is a different behavior that the process have in these two cases, okay? One of the cases will be close only to 0, and the other case will be will be stable on far from 0, okay?
You want to say that the picture will be the same when you choose n is equal to 2000?
Yes, yes. Yes, exactly, so yeah. Yep.
I don't really need this, but so why do they stabilize around 1? I mean, I thought they could grow as much as.
No, because in this model, the actors, the social pressure of the actors is set when there is present opinion. So it kind of can't grow in to infinity because the actors, their social pressure is resetting to 0 when they're.
Oh, okay, so if I double H, I mean, everything would be the same, just twice the scale. Why are they stabilizing around 1?
What was it, the beginning of your question?
The social pressure values, they can be anything, right? They can be 55, 78. Why are they stabilizing around 1 in your model, in your simulations?
Why exactly 1? I don't know exactly why 1 is the stable point. But the point is why, so I know why they can increase indefinitely. I know that they cannot increase indefinitely because of the reset factor, okay? But you have a stable point and have only one stable point from this case.
Look at the total volume of, say, social pressure, right? Taken from all of them, each time you add H to that volume, right? And subtract, on average, 1/n of that volume, right? Because you pick one of the people with the, say, positive opinion, you eliminate that opinion, so you decrease it, but on the other hand, you give the total of H
Yes.
units of positive opinion pressure. So, but why is 1? I still
No, but this is the time axis. It's not the same picture. So
Oh,
I
no,
think,
no, the vertical axis is like.
yeah, but that's what goes on with time, and I think that he takes this some mean or some value. So this is the mean value.
Yeah, so yeah, is the mean value, and for a different, so each line is a different simulation. It's a different simulation in which each line is represented the mean social pressure, the evolution of the mean social pressure on time. I'm sorry
if I take H equal to 5, or H equal to 4, right? It should be everything just twice more.
It's true.
I don't know. I know that if you take H bigger than 2, you will have another point that will stabilize.
No, yes.
But But I don't know why. I don't know what is this. Is this?
Kádmo state.
Yeah, but
His results.
really nice questions.
Well, we expressed severe interest.
Now we go back a little bit.
Sorry.
Okay. Okay, so we saw the simulation. We saw that you have these two different behaviors, and we want to study this model in the mean field framework. And there are two main results: are propagation of chaos and the phase transition. The phase transition, I think you already got what is happening. And but let's talk quickly about the propagation of chaos. So intuitively, the idea is that so the actors are interacting, and the order of interaction between the actors is 1 over n. Okay, so each opinion changed by h divided by n the social pressure of another actor. And then the greater the number of actors in the network, the lower is the effect of an expressed opinion on the social pressure of an actor. Okay, so this is kind of very clear. The greater is n, the lower is 1 over n. And then the greater the number of actors in the network, the lower the dependence between the social pressure of each pair of vectors should be, okay? So if their interaction is always 1 by something divided by n, if n is very big, the evolution of their social pressure must be more, the dependence should be lower as n increases. And then in fact, as n goes to infinity, the social pressure of an actor between jumps should follow a deterministic flow. And the limited behavior of the social pressure of an actor is described by SD. Okay, I don't think I want to be in details, but the idea is that propagation of chaos, we are seeing that we show that in a network with a lot of vectors, since the interaction is over 1 over n, each finite set of actors is independent as n diverges. Okay, and
I'm sorry. I mean, the last two sentences don't add up in my head. You say that in the limit it's a deterministic flow. On the other hand, you have a stochastic differential equation.
Yes. Yes, this I will use the next slide to explain in more details. But the initial idea is that we have a lot of vectors. The interaction is of order 1 over n. They must be independent as n diverges. Okay. So this 2 second bit more mathematic to explain. And okay. So okay. So the idea is that one can write, describe, represent the evolution of the social pressure of the actors is by using a family of Poisson random measures on R plus times R plus. And the idea is that we can write the evolution of the social pressure based on using putting the randomness of the process in this Poisson random measures. Okay, so here is just a way to write the model. So we rewrite the opinion, the social pressure of time t is the initial social pressure. Okay, so here we are saying that the social pressure is reset each time that the actor expresses one opinion. Okay, and we are checking if the actor expresses an opinion using this Poisson random measure. Okay, so we are using this. Check the times in which the actor expresses an opinion, and when it's expressed, his social pressure is reset to 0. And here we are considering the effect of the other actors in the social pressure of actor A. Okay, so what we are saying is that we check each time the social pressure, one actor expresses an opinion, an actor different from A. We check what is the opinion that can be +1 or -1, and we change the opinion, the social pressure of actor A by A divided by n. Okay, so this is just a different way to write the model that I described using this Poisson random measures to represent the process. And the idea here is that, so what I was saying is that, okay, the actors must be independent when n diverges. And here we have, something divided by n, okay? So, and this is the same thing for all actors, okay? It's the same term divided by n, but summed for the actors different from A, okay? So, the idea is that when we suppose that all the actors, the initial social pressure of the actors are IAD sequence, we believe that large numbers must be valid for this term here, that is the sum of something divided by n, okay? So we believe that in the limit, as n diverges, this will be replaced by the mean, okay? So in the limit, what we have, the limit, the equation that must describe the social pressure of an actor in the limit will be the same thing here, okay? The initial pressure here, the receptor term is the same, but replacing this by the expectation, okay? So this is the idea. The idea is that using independence, we believe that law of large number must holds, and using this law of large numbers, we are able to guess the limit, the equation describing the limit, okay? And, okay. And our first result is basically that.
Some kind of mean field.
Yes, exactly. Yes. So yeah, it's on a mean field interaction here. It's H divided by M. Okay. So the idea is that okay. So our first result is that we prove what I just said, that we believe that will occur. We prove that the process is conversion to this limit equation. Okay. In fact, and we prove, so here we are proving basically that, so if we plug each actor, social pressure of an actor with a copy of the limit equation, we do the difference, so this is something that decreases with n on a certain window of time, okay? And this, at the same time, we are proving that since the actors are IID, here when we believe that since the initial conditions are IID, we are showing at the same time that the actors of a finite window of actors, they are independent, because this goes to zero as n diverges, and at the same time that they are converging to the limit equation independently. Okay. So, just to finish, I think. Até que hora aqui? Até 5 horas?
Ainda tem 5 minutos para 5 horas.
Tá. 5 horas a gente.
Você precisa de 10 minutos.
Tá bom. Okay, and the second main result is exactly the phase transition result. We already saw the simulations, we already saw these figures. So, and the idea is that the difference on the behavior of the system for these different values of H, okay, we should be able to see this difference when we study the invariant probability measures of the equation describing the limit behavior of the system, okay? And okay, so
you're talking about the phase transition?
Yes. Yes, okay. So the idea is that the two behaviors we saw, we can be somehow seen on the current measures of the limit equation. And the result is this one. So when we suppose that the phi has a very particular form, okay, so we are basically supposing that our function phi for our phase transition result, we are supposing that the function phi is something like that. So it's always increasing. Very good. It's always increasing. It's kind of is a sum of a value and the odd function here. So it's a kind of a symmetry here. and the derivative is always decreasing, something like that. So we have a lot of assumptions that is a kind of restrict the form of this function phi. But the idea is that under this restriction, we can prove that if age is small enough, smaller than a certain threshold.
I guess it is it's a second derivative in the first problem.
Yeah, I was thinking about the same.
You're saying that it's convex.
Yes.
No, it's the first, yeah. No.
So the second derivative is negative.
No, that's right, yeah. No, okay. But the idea is that we can prove that we have a certain threshold, that below the threshold, the limit equation has only one probability invariant measure, that is the invariant measure that puts the mass only on the zero. And above the threshold, there is two additional non-trivial invariant road measure, one that has support on the positive real number, and the other that is a symmetric version of this positive invariant measure around zero. Okay, so okay, so this explains why we have this different behavior. Okay, below the threshold, the only invariant measure is around zero, so that's what we saw, the threshold pressure being all close to zero. And here we have two, one positive, one negative, and that's what we saw some simulations going close to a point in zero, and the other going close to a point, a negative point. Okay.
Expression for the invariant measures or just the existence?
I have. Okay, let's. No, I'm skipping all of this, but let's focus on the. Where's theorem 4? No, I don't have here, but.
You can derive the.
Yeah, but it's not explicitly, in fact. So it's implicitly, because yeah, no.
So you prove in some sense the existence.
We prove the existence, and we prove. Yeah, but yeah, no, but we don't have it explicitly. It's implicitly given. Yeah. But the fact is that under these additional assumptions is exactly the assumption which we can find the invariant measure value is explicitly, but in general, no. Okay. And anyway, I don't have it written here. So yeah, so this is our main results. I won't say anything about the proofs. I want to say just about the end here of the presentation. Okay, so our results is that we have phase transition and we have propagation of chaos, and we proved that, as you can see on the paper, or we can talk later. But anyway, so I would say a little bit about the next steps after this article here. The first step that is very interesting is that we believe that the system has a metastable behavior. Okay, that is something that so we see that above the threshold, the system quickly goes to one of the poles, the positive or negative. But we believe that in fact the system it will interchange between the positive side and the negative side in a metastable way, meaning that as n diverges, the time in which you have to wait to see the system going from one state to another is an unpredictable, random, long random time. Okay, so and we see that because in simulations when we don't take so much actors, so here with 200 actors, and with age a little above the threshold, that is 1.4, so in this case, we can see the system being a long time around the negative stable point and quickly going to the positive positive attractive point, then going from the positive to the negative. And then, so we have evidence, and this is one of the next steps that we are working now to prove that the system exhibits ability in the above the threshold phase. So as we see, we prove the phase transition on the very non-general assumptions that phi is very very restricted, but we saw in the simulations with the exponential of R that the behavior is the same, with the same threshold. So we believe that the phase transition holds for a wider class of functions phi, and this is something that we want to prove too. Last 5 minutes, I want to say a little bit that, okay, so from the ones who know the Gauss-Rochambeau model, it's clear that this model is inspired in the kind of on the Gauss-Rochambeau model. And, okay. So the idea of the Gauss-Rochambeau model are modeling a set of neurons instead of social actors. And these social actors, this set of neurons has a membrane potential instead of social pressures. And these neurons, they spike instead of expressing opinion. And the spikes don't have directions, only a spike. And the spikes change the social pressure, the membrane potential of the other neurons by a certain quantity that is described, that is the synaptic weights. And this is the Gauss-Rochambeau model. Is very it's like don't have directions. It's like the model that I presented, but without the directions. Only one direction, only the spikes. And so on this class of the GL model, this question of field of the propagation of calls and mean field limits are very much of interest. So we have there are some results on this direction, and then one of the next points, the next idea too is to see with the way we prove the techniques we use to prove our result can be used to the Gauss-Rochambeau model to prove similar results that in a more in a more general framework. Okay, so. So there are a few articles that study these questions for the Gauss-Rochambeau model, and we would like to contribute in this framework too. Okay, so this is a paper that is about to be published with Eva Lacherba. It's on archive. You can see that, and if you have, it's about to be published. And thank you for your attention.
So if there is any questions?
Yeah, but yeah, don't you?
No, we should do it because there's people on YouTube watching.
Oh, I see. I see. I'm sorry. So on that metastability slide, in one of the lines you said h equal to n, but I thought, h is fixed and you increase n, and I still don't understand. Like the last line.
Oh no, sorry. Yeah. So this so there is another. So if we prove metastability on this concept, we will be on the same direction of another article that I did with Gauss, in which we prove metastability, but not in the not on the mean field framework. Okay. So for this article here that prove metastability, it's like we have h equal to n because we are not on the mean field framework. Okay. The actors give a certain one. Okay. Yes, one. And And we consider only the phi as a function that is exponential of beta r, and we study metastability when beta diverges, okay? And for this,
what about n? N is
n is fixed. So in
n
this
is
case,
fixed.
in this
So
phase,
you have finite fixed number of actors, and each time.
yeah, but
I
this is other. Sorry, this is other work. This is already done. I just was saying that metastability is interesting in this context, but on the concept in which I presented now, it's a mean field framework divided by n and n diversion. This is the framework we saw now. Yeah. Sorry, I should have said that.
Oh, but I mean, again, in that paper, like each time if you have positive value of use, and you definitely say +1, and if you have negative, then so there's not going to be like expressing the opinion opposite from the social pressure that you have, the sign of social pressure that you have.
Yeah, no, it follows the same mechanism of opinion exchanging, but not in the mean field framework and with a finite social network.
So in this slide, you believe that you have metastability in this model also, in the mean field approach, because of this kind of simulation, right? But how you're guessing this phi? My question is, what is your hypothesis about your firing rate? Because it's not by luck that you took this term, right?
Yeah,
this function.
So this phi
So-
is inside.
Satisfying the condition of the mean field.
Yes, this phi satisfying this shape here that in which we prove
So this is
the phase transition.
Your hypothesis for this phi function is the same that okay.
Okay, yeah. So yeah. Yeah, so this is the condition which we proved. We believe there is more general, but we proved for these conditions. Okay, so that function satisfied is 1 plus the hyperbolic tangent satisfied these conditions, and well, we on simulations we can see these changes of regime, but it makes sense too, because when we look at the model with a finite number of actors, it is it has a unique invariant measure, so we will visit all the points, it's positive recurrent and so on. So if the model has a high tendency of being on a side, on a direction, that it's what the invariant measure indicates, so we know that eventually it will go to the other side. Okay, so prove that so it makes sense also because of the behavior of the model for each number of factors.
So do you think that the condition that this F has to be antisymmetric is necessary for the theorem to hold, or it was just simple to do that way?
No, it's just simple to prove that way. It's just.
But it will probably hold as well if you have any other function without the third condition.
Yes, because the simulations we saw, we consider the phi exact phi of r equal to exponential of r. That is not symmetrical, is unbounded, and the simulation indicates that the phase transition holds for this function too. But the case is that what happens is that to prove that, we kind of have to solve a fixed point equation, and these are the conditions in which we could solve explicitly this equation. So it's just a mathematical, a technical thing.
But maybe if F is not antisymmetrical, maybe then in the phase where you have two non-trivial invariant probability measures, you will maybe have only one. No. Because I guess so if it's not antisymmetric, I guess you'll be pushed toward one side or the other. It doesn't make sense?
No.
No.
Because, even the phi being antisymmetrical, the rates in which the actors express opinions follow the symmetry. Okay, so this is phi minus r, phi of r plus
Oh, yeah,
phi
yeah.
minus r. So the model is always symmetrical in the sense that, but the phi don't need to be symmetric to that for this holds. Okay.
Okay. And I have just another question. So, propagation of chaos, does it mean, what is the definition? It means that basically the mean field approach is justified. Basically, this is the meaning of propagation of chaos, is that it?
Yeah, it means that for each finite set of actors, so we have a system with a lot of particles, we're studying the behavior of the system when the number of particles increase. And it means that each finite set of actors, they become independent as n increases. Okay, and
yeah. So basically, it means that the mean field approach holds for big N, right? This is the meaning of propagation of chaos. Just
what you said,
it means that the mean field approach actually holds for N big enough.
Hold for N big enough. What do you mean?
Well, when N goes to infinity, you have mean field.
Interactions by the mean. This is the point. And then everything behaves the same, like independent particles, the same mean.
I'm just trying. What is the difference, like the semantical difference between propagation of chaos and mean field? It's the same thing basically. It just means that propagation of chaos just means mean field. No?
Mean field limits is the limit is the study of the system in this behavior, but the propagation of chaos is the
result of the mean field.
Yeah, it's the fact that
you have a mean field, and then your interactions are becoming smaller and smaller when your system is bigger and bigger. You, in some sense, you lost the interactions.
Okay.
Then it's chaos. In some sense, it's like
each particle is independent of everything else, and that they are behaving independently. Like, for instance, Poisson point processes with the same mean. They are behaving as the mean, but this is a consequence of mean field. It's not the same.
Okay, to me this was a definition of mean field. But
no, it's a consequence.
It's
because in some sense, the mean field, when you send n to infinity, your interactions are becoming smaller and smaller, and then in some sense, everything becomes just as the mean.
Okay.
Thank you.
Olá. Deixa eu começar com alguma coisa que aparentemente não tem nada a ver com matemática. Você está agora lá em Ribeirão Preto, né?
Sim.
Você mostrou esse resultado para Fernando Prado?
Não.
Então. Então eu posso falar alguma coisa?
Sim.
Tá. Eu acho que no ano 2000, o Fernando Prado, ele era meu aluno de doutorado. Eu não fiz nada naquela orientação. Ele achou tudo sozinho, né? E um dos resultados dele era exatamente aquilo. O modelo é um pouco diferente, mas o resultado dele é muito parecido com isso que nós estamos aqui. E também ele pegava o que eu acho que chama-se mean field, quer dizer, ele dividiu pela quantidade de agentes e mandava esse n para infinito, né? Então, no final das contas, toda a parte estocástica morria. Não sei se aqui também morre ou não, mas tá. E ele ficava com um sistema dinâmico. Nesse sistema dinâmico surgiu essa função que você desenhou aqui, e dependendo na dinâmica desse sistema, o que acontecia aqui, essa função ela andava para a esquerda ou para a direita, e a diagonal determinava quantos pontos de equilíbrio tem esse sistema dinâmico. Para ter um ponto de equilíbrio para qualquer posição dessa sua função, precisava ter aquela condição, certo? E aí, quando ela está quebrada, aquela condição, então, tem dois pontos de intersecção, e aí o sistema vai ou para lá ou para cá, tá? Então, ele mostrou esse resultado. O modelo dele é um pouquinho diferente, um pouquinho mais simples que o seu, mas eu acho que eu não consegui agora acompanhar tudo para poder te dizer se é a mesma coisa. Acredito que não, mas quando eu vi o teorema e a função que você desenhou, eu senti que é basicamente a mesma coisa. Isso não é uma novidade muito ruim, porque ele inventou outras coisas. Então, no modelo dele, não sei como que introduziram isso no seu modelo, mas no modelo dele, os agentes eram suscetíveis à influência dos outros. E também eles tiveram, cada um teve uma avaliação individual do valor da ação, digamos, que ele poderia comprar no mercado. Tá? Então, ele era suscetível ao valor da ação e à influência dos demais, né? Era um modelo para compra e venda, não? Diferentemente do seu. E aí, então, tem essas duas influências, né? Porque os agentes compravam, vendiam, isso mudava o preço, e em função de mudança de preço, lá no sistema dinâmico, essa função ela andava para a esquerda ou para a direita, né? Mas também tinha aquela influência, social influence, né? Quando ele, meu aluno, quando ele analisou esse social influence, lá tem um outro efeito, tem uma outra função, que é a função de susceptibilidade, que ela entra no jogo. E lá, quando você considera essa susceptibilidade, ela sempre tem transição de fase, não tem condição para não ter transição de fase. O que é interessante é quando você mistura a influência social e a influência pelo valor da ação, que você no seu modelo ainda não tem, né? E aí começam a surgir coisas bem interessantes. Tá? E que eu espero que, se você conversar com o Fernando Prado, ele vai poder te explicar tudo isso. Tá? E aí talvez você vai conseguir introduzir no seu modelo algumas coisas mais, assim, alguma coisa a mais, né? Mas essa condição e essa função surgiu pela primeira vez, ele achou pela primeira vez num artigo de 1984, se não me engano, numa revista de economia, de um economista conhecido, que eu esqueci o nome dele agora, que ele falava o seguinte, ele falava lá sobre uma cidade lá na Califórnia, e ele falava por que tem dois restaurantes quase que iguais, né? Tudo quase igual, mas um restaurante é sempre cheio e o outro é sempre vazio, né? E aí ele tentou explicar isso usando transição de fase, e o desenho dele era exatamente esse aqui, e aí tinha lá uma diagonal, né? Aquela coisa que cortava em 2 pontos. Ele falava que esses são 2 pontos de equilíbrio, nos quais um deles corresponde a vantagem de um restaurante em relação do outro, né? Então, o que eu posso te dizer? Que aqui tem como, eu acho que tem como sofisticar o modelo, andando pela direção já assim, traçada pelo Fernando, e talvez você vai ter nesse caminho alguns resultados muito interessantes. Tá? Mas, de novo, eu peço desculpas se eu não consigo, assim, logo de cara, te dizer em que medida que o seu modelo é parecido ou diferente daquele que foi estudado por ele por uns bons 10 ou 15 anos. E ele tem muitos artigos publicados, mas a maioria deles nas revistas de teoria de jogos, porque ele traduzia esse comportamento de agentes em termos de função de utilidade, levava tudo isso para a teoria de jogos e publicava nas revistas dessa área. Eu falei português, né?
Melhor que o russo, né?
Melhor que o russo, pelo menos isso, tá?
Can you repeat again in English? Obrigado, eu vou ver isso. Obrigado.
Então, let's thanks again, Kádmo. E então terá mais um seminário em dezembro, antes do verão. Não sei ainda exatamente a data, preciso entrar em contato com o Osame, que provavelmente será o a pessoa que vai fazer a palestra. Isso. Obrigado, tchau.